Thank you. So this talk, I skipped the introduction. So this talk is about connected vehicle, and Gaurav should have been here. He's one of our customer. He's working for a leading automotive vendor. He couldn't be here for visa issue, not coming into Germany, but getting out of US. Where US? Anyway, the talk will be more powerful with him, but I try to chug along. So this is coming from a real use case with them, and the requirement is in part simple. They have tens to millions to hundreds of millions of vehicles potentially, and all these vehicles are streaming telemetry data, a lot of telemetry data, high volume, and they want to stream to the cloud to do analytics, and they want to also use this channel to do real-time control. So send commands to the vehicles to do any kind of logic there, and they want to have kind of the data plane goes to cloud, control plane goes from cloud to vehicles. So telemetry data is very high volume, and but control data is low volume, but it's very critical. The commands cannot be missed; they have to be retried. They have to be stored for potentially days or weeks, and there's a logic to detect if a vehicle does not come back online. And we have to kind of like also track the delivery that this vehicle has really applied those commands and so on. And that each device needs to be addressable individually. So you have to have a channel for each of these vehicles, so hundreds of millions of channels potentially. With no broadcast though, which is nice. The other requirement is MQTT. So MQTT, I mean, as one knows, it's a hard requirement for any IoT use cases. And in their case, they had already tens of millions of vehicles using MQTT. And they cannot change that firmware that is in the vehicle. And also, it's not plain MQTT. They have extensions, some extension to the protocol, some modification to the standard, so that we also have to take care of. Going back to Pulsar, I give you a very high-level introduction of Pulsar for those of you that don't know Pulsar, and how does it fit in this context. So Pulsar is a flexible PubSub and compute base backed by a durable log storage, and kind of like a main selling point for Pulsar are durability. Data is always replicated in multiple nodes. You can decide how many, and f-sync to disk. Latencies are typically around 5 milliseconds, 99%, can be lower even, some trade-off in the configuration. And even it's a partition system, so you can have topics with multiple partitions, but even on a single partition, you can reach up to 1.8 million messages per second. The system is highly available, on the write especially, very different from architecture from other systems. If you have any two storage nodes available, you can write, you can publish messages, even if you lost 98 other storage nodes. It's cloud native in the sense that it is designed for an environment where we can scale up and scale down the clusters very frequently. There's a unified messaging model. I will expand a little bit on it. Highly scalable. We can have millions of topics. We also have a native compute, which is like lightweight compute function framework. You can submit a function on the cluster, and it will run it for you. And it's multi-tenant. It was designed to be multi-tenant from the beginning. We designed this at Yahoo. We had one single cluster for the whole company. We had hundreds of teams using Pulsar cluster without making a mess between each other. And also we have support for geo-replication out of the box. So typically deployment can be from 1 to 2 to 15 clusters in all around the world. I spoke about messaging model since there are a lot of messaging people here. I just want to get a bit on this. So Pulsar has a topic very similar to anyone else. You can publish on the topic, and you don't have to care about how the data is going to be consumed. a topic can have subscriptions. Subscription can have different types. So, and subscriptions are independent between each other. You can have exclusive, one consumer only, order delivery, failover. You can have multiple one active order delivery. Shared is purely you can have as many consumers as you want on the subscription. A round-robin delivery is basically this is what you can implement a queue. We also have this key share, which is a hybrid mode, which is you can have as many consumers as you want. You can have them come up and down, in and out, and we have guaranteed per key delivery. So you can basically we use consistent hashing in between. We track whatever was act, what was not act, and we can have this scale up, scale down with order delivery. Architecture is again just a couple of words is a bit different from other messaging systems. We have two layers in the system: brokers that are stateless, or they have no durable state. Better said, topics can fail over from different brokers without copying any data very quickly. Then we have Bookkeeper, which is a storage nodes. Storage nodes, it just pure store data, multiplex for multiple different topics. There are multiple advantages for this architecture. You can scale these two layers independently based on if you need more brokers for storage capacity or if you need more storage. Failover is very quick. You can just add more nodes, more brokers, and we can fail over topics to these brokers without copying data. We can add storage nodes, and they will gradually receive more data to store. There is no rebalancing like in Kafka or other systems, and we can scale up and scale down very easily. Finally, Pulsar is multi-protocol. There is support for the same topic model can be accessed through multiple protocols. So we have our own native protocols, which we have all our features, but we also support Kafka protocol, MQP, and MQTT protocol. So you can interact with the same topic using different protocols. So you can say publish with Pulsar, consume with Kafka, or the reverse, or send with MQTT, consume with Pulsar. This is just a brief note of benchmark. I know people love or hate benchmarks. This is one. This is one we did with between Pulsar, RabbitMQ, and Nuts. And kind of like first one is like the throughput. So this was on a 3-node cluster, so small one. Throughput on a 50 topics. Upright is consumer throughput, like training backlog and so on. Latency, lower is better, and max fan out on a topic. So how many subscription, how many X is out compared to 1 X in. You can scan the QR code. There is the full. It's like 20 pages. The report, all the criteria, what we went through there. Is if you are into these kind of things. Next one. We started the journey a couple of years ago, actually 3 years ago, to replace Zookeeper. That's pretty common to be hated system all around the world. But basically, we've been using Zookeeper as a coordination and metadata. But Zookeeper has few limitations. Basically, each node has to have the entire data set in memory. This is one. You cannot scale horizontally. His throughput is limited, but also his data size, because everything is memory, it is limited. Also because it takes a snapshot of everything. Each time it takes a snapshot. So after like 1 gig or 2 gigs of metadata, you are out of luck of scaling a Zookeeper up. So with Pulsar, we can reach few million topics, but at that point, Zookeeper becomes the limiting factor. We cannot have more metadata in Zookeeper. That's the bottleneck. So we're embarking in this journey of creating a new metadata store and coordination system to provide similar functionality as Zookeeper and etcd. Basically, the design has been to remove all single node limitations. And also, one key aspect was designed for Kubernetes. That's because we don't deploy on bare metal, almost never. So try to take advantage of new Kubernetes as the base environment rather than bare metal. We want you to have transparent horizontal scalability, just keep adding nodes and have more capacity. And we don't need fully linear Heisenberg history across all the data set. We just need per key. per key linearizable operation, with millions of writes and reads per second, and store hundreds of gigabytes of metadata. This is not for storing data, this is just from metadata. And coordination. And a month ago, Oxia has entered the CNCF sandbox. So it's been open source since the beginning, but we're trying to form a bigger community in CNCF for Oxia. Architecture for Oxia is pretty much straightforward, I would say. There is one, so we have storage nodes. Storage nodes will hold shards. You can think of this as a big key value store. Clients will have a server discovery. We figure out which server has their shard that they're talking about for this key. There is a coordinator. The key part of the architecture here is that we're not using Raft for replication of the data. We are using basically log replication. This is very similar to what Bookkeeper does. And if there is any failure, the coordinator is the one that will trigger literal action and resolve all the conflicts between the different nodes. And it will checkpoint the cluster status in the config map. So this kind of like pluggable consensus that is only applied when there is a failure. So when there is a literal action, then we have to checkpoint, for example, the epoch and so on. So the tying back Oxia to IoT here. We designed Oxia to replace Zookeeper, but then while maturing Oxia, we figured out that we can use this for many other things. Before, we couldn't use Zookeeper for any intensive updates because it doesn't scale. But now we have a scalable data system, so we can do things in different ways. So we started thinking, what can we add to Oxia that will make our life easier? And we came up with new features in there. One is sequential keys and or secondary indexes, or also we have this fast notification. Secondary indexes, I guess everyone knows what they are. Sequential keys are, it's not like any esoteric thing, but it's kind of like a way to have the key value store to atomically assign keys based on arbitrary integer sequences. So this is very useful if you want to generate unique offsets, for example. And if your offset also, you don't want to always increment by 1, maybe you want to increment by 2, the batch size, for example, or the size of the batch. And you can have multiple sequences within a single key. So you can have 001 dash 001 megabyte, for example. The key here is that you can assign ordering without having your data to travel to a single node. Here, only the metadata will travel to a single point in Oxia. The unique part is also that you can subscribe to updates for keys for a specific sequence. If you do the math here, you can see that you can build a queue on top of this, right? It's kind of like a very similar to a queue. So you have some way to atomically assign ordering to events, and you can also subscribe and receive all the updates for a channel of events. Going back to MQTT, so we need a way to address each vehicle individually. So we need one MQTT topic per each vehicle. So in Pulsar, typically we map one MQTT topic to one Pulsar topic. Now, Pulsar can scale to millions of topics. With Oxia, we can scale to 10 million topics, 20 million topics. Fine. That's not hundreds. And also that even if it's possible, doesn't mean that is convenient or if it is the most efficient way of solving the problem. Because essentially when you have a Pulsar topic that is all about writing data on a log as fast as you can, in this case, we have hundreds of millions of logical topics with very small throughput on each of them, very sparse events. So using one Pulsar topic per each of the vehicle, even if it were feasible, not to hundreds of millions, but it will not be efficient, and we need a better solution for that. So tying everything together, we come up with this in our MQTT implementation with the concept of virtual topics. Essentially, we map multiple logical MQTT topics into one physical Pulsar partition topic. It's like multiplexing the multiplex. Not rocket science. But so on the injection, it's easy. Just use the key as to retain order, and then you can kind of like have all the vehicles send telemetry data into this partition topic, and then you can like run streaming analytics pipeline and consume all this data and run some analytics on it. On the dispatching becomes more involved, right? So we have basically a single topic to receive all these commands for hundreds of millions of vehicles, and then we have to kind of like control whether these vehicles have consumed the data or not. And it can be days, weeks, and so on. So essentially this MOP, which is our MQTT protocol, kind of like reads from this Pulsar topic and then demultiplexes it into Oxia, using these sequences and approach. So there is one sequence per device, but this is a way lighter weight than having a full-blown log-based Pulsar topic per device. It works as follows. So if you have a new device or vehicle that connects, it will first check into the available queue in Oxia for any available events, commands that it has to download through MQTT, or it will basically use the sequence notification to get new events. So this is kind of like how everything got tied together, and I think this is like an interesting use case with like a very practical and is both generic and specific to vehicles. But I think it was a good way to show that what can we achieve with Pulsar MQTT and at a large scale. And the advantages typically is that for the user, where that they have a single platform that can handle everything. They don't need an MQTT broker that have to fed some other messaging system that will have to fed some other streaming analytics. Basically, we can have the MQTT and the messaging in the same service. You don't have to duplicate data. You don't have to integrate those two systems in a way. And you can run streaming analytics directly out of it. It is easy to operate. You can scale up and down very easily, add more capacity or reduce capacity when you don't need it. That was the last one. I don't know if we have time for a few questions. I'd be very happy to answer. Thank you.
Any questions? So thanks for the talk. If your client language of choice, coming over from Dreamtracks, does not have a native adapter for Pulsar, which protocol would you suggest we would be using, like either Kafka or AMQP or to consume a queue, to be more precise?
There are many language bindings for Pulsar. There is an Erlang-based one. Yes, I haven't tried it, so I cannot comment on the completeness or the quality, but there are many. Otherwise, and I would say it depends more. Like if you say, should I use Kafka to send or MQTT or MQP? It really depends more on your application, what you're trying to achieve, and what's the style of your application, or if you're familiar with any of these SDKs. Probably easier to go with that.
Any more?
So I assume what you just discussed were persistent sessions, right? So how do you deliver queued up messages back into
yes.
client? What do you do when the session expires?
The session for the vehicles. Then basically the topic. So that logic itself is on depending on the control. So the data will stay there until it gets either consumed and acknowledged by the vehicle, or some admin will just clean it up.
Okay, thank you.
Any more questions for Matteo?
Just a quick comment.
EMQ built the Erlang binding for Pulsar.
See.
Matteo, thank you very much.
Thank you.